In this video 1-3, we will be looking at real numbers and the number line. By the end of the video and work time in class, you should be able to say, I can classify, graph, and compare real numbers, and also I can estimate square roots. So in the vocabulary, what is a square root? A number a is a square root of a number b if a squared is the same as b. So basically what this is telling us here is if I was looking for the square root of b, I really want to know what squared gives us b. What squared would give you the b? And we'll look more here in a minute at some square roots. But the radical symbol is the symbol we use when we're looking for square roots. You may check your calculator or a calculator application you may have on a smartphone or iPad, and you would see this here as the radical symbol. That will help us find a square root. The radicand is the expression under that radical symbol. So whatever is underneath is the radical, or the radicand, and the radical is the radical symbol and the radicand to form the radical. So the whole problem itself, the symbol and the number underneath is the radical. So some examples here. The square root of 25. So that would be the square root symbol there is your radical symbol. The radicand is 25. The whole thing is a radical. And so what we're trying to figure out here is what number squared gives us 25. So what number squared gives us 25? That would be 5. Square root of 4 over 81. And we're going to look more at some more complex radicals later in the school year, but this is another one similar to number 1 that we're going to do. We're not going to get too much crazy other than this. What you want to do is you want to split the numerator from the denominator and think to ourselves, okay, what squared gives us 4? What number squared is 4? Well, that would be 2. And then what squared gives us 81? That's 9. The square root of 81 is 9. So the square root of 4/81 is 2/9. Now what works nice is when the number underneath, which is the radicand, that number underneath the radical symbol, if that's a perfect square, it's really slick for us to figure out what the square root is. So the square of an integer is a perfect square. So we're going to make a perfect square list. So 1 squared we'll start with. 1 squared is 1. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, and we'll stop at 15 squared, which is 225. These are perfect squares I would like you to have memorized. So these are perfect squares, which essentially means, like, for example, 36. I could make a square, a perfect square, that would have 36 squares inside of it, and that would be 6 by 6. I can make a perfect square that has 81 squares inside of it, and that would be 9 by 9. So we can make a perfect square with that many smaller squares. What is the appropriate side length of a square that has an area of 220 square inches? So if we have a square, and it says appropriate side length of a square that has an area of 220, well, 220, that's not a perfect square. So we look at our perfect square list and we see that 220 would fall between 196 and 225, and it's closest to 225. So if it was 225, and the square root of 225 is 15, because 15 squared is 225. So that means the side length, what it would be appropriate, would be approximately 15 inches. And that's inches, so let's label that I-N. So approximately, and once again I'm putting the approximately symbol in front of the 15 because it said 220, which is not a perfect square. A rational number, we're going to define different real numbers here. A rational number is any number that you can write in the form of A over B. Natural numbers start with 1, and then 2, 3, dot, dot, dot. Goes on forever. We're not dealing with parts of wholes here. We're just working with 1 and up. Very similar to whole numbers. Whole numbers start with 0. We don't have any decimals or parts of wholes. Integers, we're dealing with whole numbers and their opposites. So 1 and the opposite, -1. 2 and -2. 3 and -3. Irrational now cannot be written in the form of a fraction. They cannot be represented as a quotient of two integers. In decimal form, they do not terminate or repeat. That means they go on forever. An example of an irrational number, one of our more well-known ones, would be pi. The square root of any non-perfect square, like the square root of 2, that would be irrational. The square root of 220, we saw that that wasn't a perfect square. That would be irrational. They go on forever in the form of a decimal. They don't repeat or end. Real numbers are all of these defined above. A real number are any rational or irrational numbers. So we have to see which subsets of the real numbers each belongs to. 12. 12 would be natural. It would also be a whole number, an integer, and rational. Rational because it can be 12 over 1. It could be 24 over 2. An integer, it's a whole number. It's a whole number. We don't see decimals or parts of wholes. And it's natural. -5.01479. It ends. It has a definite end here. It doesn't go on forever. So that makes it rational. Because as a decimal, it's not going forever. It has an end. So we know if it's rational, we would be able to write it as A over B. The square root of 21. 21 was not in our perfect square list that we wrote up to 225. So 21 would be irrational. An inequality is a mathematical sentence that compares the values of two expressions using an inequality symbol. Less than, greater than, less than or equal to, greater than or equal to. So we should be able to compare the square root of 3/4 and 5 4/5. And I like to put them both in the same form. I'm going to put them both in decimal form to compare. The square root of 3/4, that would be irrational. We get 5.830, and it goes on forever. And we're going to compare it to 5 4/5, which would be 5.8. Well, they both have 5 in the ones. They have 8 in the tenths. But in the hundredths here, there's a 3, and over here, there's a 0. And that 0 is smaller than the 3. The 5.83 would be greater. The alligator eats the bigger number. So the square root of 3/4 is greater than 5 4/5. We're going to order. We have the square root of 9.3, 0.3, negative 1/4, the square root of 3, and negative 4.25. What I like to do is put them all in the same form. So I'm going to put them all in decimal notation. We've got the square root of 9, and then we have 0.3, which is 3/10. We have negative 0.25, the square root of 3, which would be irrational because 3 is not perfect, or is not a perfect square. So that'd be about 1.73. And then we have negative 4.25. Now we know the bigger the negative, the smaller it is. So we're putting them in order from least to greatest. So the biggest negative is negative, let's see, we've got negative 4.25. And then our next negative would be negative 0.25. That would be bigger. Once again, the bigger the negative, the smaller it is. Now we have positive values. We have 3, which is a whole number, 3. And 3 wholes is going to be more than 0.3, which is 3 out of 10, 3/10. And we have 1.73. Well, we have let's see here. Something just popped up on the screen. So we have 0.3, there we go, 0.3 is going to be smaller than 1.73, 1.73, because we have one whole and part of a whole, and then 3 would be our greatest. So in order of how it was written, it would go negative 4.25, and then it would go negative 1/4, and then it would go 0.3, the square root of 3, and the square root of 9. That would be in order from least to greatest. So what helps us to do that is to put them all in the same form. Remember, the bigger the negative, the smaller it is. Looking at parts of wholes and wholes to help us order. Can you say, I'm moving that here, can you say I can classify, graph, and compare real numbers, and I can estimate square roots? Write 2 to 3 sentences on today's lesson, and what are your questions? Write them down and be prepared for the work time in class.